All right, I'm gonna go ahead and get started. So what I want to try to tell you a little bit about today is some things that I've understood about this paper, Transformers Learn Shortcuts to Automata. I'm gonna tell you at least the parts that I understand today, and then hopefully I can tell you about the rest of what I don't understand by next time. Okay, so this paper is about implementing semi-automata with transformers. So let me just remind you what a semi-automata is. Okay, so this is a deterministic model for computation. So I think before I mentioned finite state automata. Those are essentially semi-automata, but without any kind of outputs from it. So at least this is how I understand it. So I think when I discussed finite state automatons before, so you have a finite set of states, you have a finite set of actions or a finite alphabet of elementary transitions on those states. And then also there's an extra map that tells you at the end, kind of associated to each state, there's some sort of output. And you can use this for example, binary classification or multi-class classification. So a semi-automaton is the following. So it's I guess so it's a triple Q sigma delta, where Q is a finite set of states. Sigma you can view as a finite alphabet. And you should think of the elements of this alphabet as representing elementary transitions between states. So I'll write that too.
Ellie, sorry to bother you. Can you move the camera to the left 1 inch?
Let me look at the way that I see. Yes. Thank you, Caleb.
Thank you.
Is that better?
Perfect.
Yeah, thank you. Okay, so sigma, the finite alphabet of elementary transitions between states or on states. This may be a better way to say that. And delta is the function that implements these transitions. So it takes in a pair of a state and a transition, and it outputs a state. So let me just give an example that will be important later, not today, but probably next time. So let's let the states in a particular finite state automaton be pairs of integers. And let's let sigma be these 4 elementary transitions. So a nice geometric model of this automaton is the rectangles in this grid. And you can imagine if you start at a point labeled by this horizontal index and this vertical index, you act by one of these, you'll move within this grid. And then the rule is when you're up here, if you get hit by this, then you stay. Okay, so I'm not going to write down all the transitions for that semi-automaton, but so this is sometimes called, well, in this paper, it's called 2D grid world. So, yeah, the point is that now also if we have length T sequences, so we're imagining that we're going to use transformers to implement these automata. So in a transformer, you always have the context length, and in this case, the context length will refer to the length of the string in this finite alphabet. So let me just make that explicit. So for all T and N. So now if you have a length T sequence in the alphabet, you get a length T sequence of states, which is just acting in turn by each of the, so you start with the initial state Q0. And now if you have a length T string of states, instead of starting state, or initial state, and you might write this sigma 1 to T. Then you're just recording Q1, Q2, etc. So now, fix an automaton, a semi-automaton. And we let F be some function as above. We say that F simulates AT if it agrees with what I just wrote down for all pairs. Oh, I guess I should say AT up to context length T. Just for all initial states and all length T sequences of elementary transitions. Okay.
Sorry, I'm a little confused. So, like, when you say it simulates, I guess I don't understand why can't it just learn all of the transitions from this? Like, if T is at least one, like, doesn't it know how to get from like Q0 what Q1 would be, and then that tells you the whole thing?
I guess that's true. Yeah, I guess that's true.
I understand.
I guess that's true. I mean, the way the way that this is stated in the paper is actually for a particular input state and a string. So maybe and I changed it to this because I think that it's harder to simulate the transition function if you need to do it for all the states as opposed to just one. I mean, the way that this was stated in the paper is actually fixing a. Yeah, no, I think you're right about that. You're right. If it does it for all Q naught, then you kind of don't need the whole length T string. Is that right? Because you know where each of the states goes under. But I think also somehow we want functions that can take in lists like this and spit out a list like this. And so we want the function to do it for all such tuples.
So it's like, even if the function doesn't come from an atom, it's like automaton.
Yeah,
structure.
right.
It
We
might
wanted to be able to.
agree with the automaton, but it itself doesn't necessarily have to come from that.
Exactly, right. So yeah, I mean, the point is that actually one thing that I'm not quite clear on yet in this paper is whether the constructions they give. So yeah, let me sort of say where I'm a little bit confused about what they've done. So when they write down this definition, they're talking about mapping length T strings of states to length T strings length T strings of transitions to length T strings of states. And they're talking about doing it for every, so for a fixed state. And so fixed initial state. But it's much harder to do it for all of the states at once than it is to do it for a particular state. So I hand you a state, you give me a construction that will simulate the automaton in the sense that if you hand me a length T string of elementary transitions, then it will map you to the appropriate kind of path for that initial state. That's a much different, that's a much less robust construction than being able to do it for all of the states at once. So that's why I want to write down this more strict definition. Okay.
Thanks.
So I think where I want to start is just to remind you, and I never kind of gave a construction, and I probably won't ever really in this class, but I want to, yeah, because it's somehow not as much of interest anymore. But I do want to remind you that actually some of the initial work understanding neural networks was around the fact that they can represent semi-automata and even Turing machines. So historically, in any semi-automaton, A in any context length T, there exists a recurrent neural network have tilde that simulates a up to context length t. So I just want to, I think this result goes back all the way to Minsky in 1954, although probably this used sigmoidal activations. And then there's a paper of Siegelman, which is on my reading list, and it's actually pretty nice. It's a sort of succinct construction. And then Siegelman's on that. So I'm not going to really give details here, but what I do want to tell you is what the structure looks like for these recurrent neural networks and how it is that they're simulating automata. And also what I would say is kind of the fundamental geometric tension here in representing these kinds of computational models with these sorts of architectures. So just want to recall the structure of an RNN, mostly because I want to draw a contrast with the structure of a transformer. So the idea here is that you have two fundamental vector spaces, an encoding space for the states and an encoding space for the sort of a representation space for the states and a representation space for the elementary transitions. And the structure of the recurrent neural network, so I'm going to just draw everything this way. So the idea is that you have the state space and you have this transition space. And you also have maps that encode the states in this space somehow. So we call these maps EQ, DQ. Same with these maps. So the idea being you somehow map the states in, they're sort of, and they land in finitely many points in here. Here's this. And so if you started with this initial state, it would land in here as a vector. And now you also have these embeddings of the elementary transitions. And the idea of a recurrent neural network is that then each of these layer maps, you would take the direct sum of the state space and the transition space, and then each of these maps is like a neural network map. So this would be determined by some parameters, and maybe it would be a ReLU neural network now, but back in the olden days, it would have been a sigmoidal neural network layer. But the point is that you're reading off the states here as the images of these neural network layers in each of these intermediate state spaces. And then And then the decoding map gets you back to an actual state as opposed to a vector. But the other piece here is that this S theta has to work for every pair, state and elementary transition. And essentially, the way that all of these proofs go is to use a universal approximation. So you have some kind of way of approximating any map on, say, finitely many points by either a single layer neural network, or maybe you need to put in some extra layers in here. But the point is that if you have a universal approximation result, then you know that you can sort of represent this map somehow. But I also want to point out that the fact that it's an approximation result, and the fact that, I mean, essentially, the other aspect of recurrent neural networks is that actually you want this map to be the same for each of the layers. So, so you're really encoding everything with this single map. And I want to point out that the dynamics of maps, of self maps like this are kind of hard to control, except up to some finite level. And that, I think, is part of the reason why recurrent neural networks haven't worked so well for in practice for actually implementing these simulations. Okay, so yeah, I'd say that there are sort of two issues with this older architecture that I'm not entirely sure have been solved by the newer architecture either, but I just want to point them out. So yeah, the first thing I would say is that although there are these theoretical constructions of simulations of any automaton using a recurrent neural network, just because you can represent a function doesn't mean you can learn it. So in other words, you can write down a set of parameters that works for implementing a particular automaton up to some level. But if you're actually trying to learn the automaton, you're training a neural network to learn parameters. And so you don't necessarily know that it's going to find those ones that you wrote down. This is a problem for somehow every architecture. And then the second issue, I'd say, is just that the long-term dynamics. I don't actually think this is well understood. At least I don't know that it's been studied by people that do dynamics. I don't know that it has. Maybe it has. I'd be interested to hear if it has.
Can you clarify what you mean by long-term dynamics? Like dynamics of what here?
So yeah, as I said, somehow somehow represent or simulating the automaton means finding a function of the form, you know, finite depth neural network with parameters theta. And so, yeah, what you want is to say that regardless of the length of the string, you can just keep on iterating f theta to determine any finite set of paths that you follow when you implement that string of elementary transformations. And I believe that at least the results that are out there only work up to some finite length. Or they're just like really brittle in the sense that you have to be kind of like right on the nose. It realizes some kind of action of points, embedded points in your space, and they have to land exactly on the set, this particular set. So anyway, I may be sort of speculating here about what's known, and maybe there's a lot more known that I'm kind of misstating, but my belief, at least based on the proofs that I've read, is that they're all kind of based on these universal approximation results, and they're typically approximations, and those approximations won't necessarily hold if you keep iterating. So let me now move to something else. Let me now define something which will seem more familiar, maybe seem more familiar to people. So there's an algebraic structure here underlying everything that we're talking about. And when you start looking at that algebraic structure, then you get a good amount of information. So you can define the transformation semigroup T of A of an automaton. So I'm going to write it like this. And then I'll explain what I mean. Okay. So here I'm talking about all finite length strings in the elementary transformations, but I'm not regarding them as strings. I'm regarding them as functions. Okay, so this is the subset of functions. Here to Q. Realizable by applying finite length strings of elementary transitions. Finite length strings in this alphabet. Okay, so So if we think about this a little bit, you should think of this as being like okay, so it's a semi-group because you don't necessarily know that these functions are invertible. But you do know that you can compose them, so there's a binary operation. And you also know that that binary operation is associative. So, right, and if you allow the empty string, then it's actually a monoid because it has the identity element to it.
So when we're getting like functions from like Q to Q instead of like Q to the T, so does that mean like taking like?
Yeah, then you take the end state, yes, yes, thank you. Yeah, I guess I'm abusing notation here. I'm definitely abusing notation here. So in particular, let me just write it down. So F maps Q0 to QT. So yeah, let me just make some remarks. Group binary operation is concatenation strings. Which is associated but not commutative. And I said this, but I'll write it too. By allowing theta equal to 0, we have a monoid. The empty string is the identity. And this I think is important to point out. That essentially what we're getting here is something like a group presentation, but we don't have the relations until we kind of examine what's going on in terms of the actual functions. So let me just write it this way. We can view the letters sigma as generators of a semi-group presentation. And relations arise when two strings induce the same function. Or you could say when the string represents the trivial element of the semigroup. When you have a substring that represents the trivial element of the subgroup, semigroup, sorry. Okay, so I mean this should really remind you somehow of, I mean, you know, whatever it is that we're going to be describing here in terms of simulating semi-automata using either recurrent neural networks or transformers or whatever kind of architecture we're going to be interested in is also going to be something about group actions or semi-group actions on spaces. So I think that that's important to also note. Simulations of semi-automata are inherently somehow induce group actions, semi-group actions. On the underlying spaces. In ways that I don't think have been fully explored either. At least I don't get the sense that they have, that this sort of connection has really been explored at length. So maybe I'll just say what the main theorem in this. Oh, I guess I wanted to say one quick thing, which I think is to note. So a sort of easy lemma. Is that if you have a semi-automaton, so always we're going to be talking about automata that have finitely many states, finitely many transitions, which I think I said at the beginning, but if I didn't, I'm saying it now. Then this transformation semi-group is finite. Okay, and the proof is that there are only so many functions from a finite set to itself. And this transformation semi-group sits inside that set of functions. So the proof is that this transformation semi-group is sitting inside of a set of morphisms on the states. This is just a set, it doesn't have any extra structure, but which has size of Q to the size of Q. You can send every element of Q to any other element of Q. Okay. So I'd say the main theorem sort of informally stated of this paper is that transformers can simulate all solvable semi-automata. I think they even give just a blanket statement, but yeah, let me just say that. The transformers simulate all semi-automata. But I think what's really interesting about what they're trying to do is actually use a decomposition of the transformation semi-group, and a decomposition of a related decomposition of the action of that transformation semi-group on the on a particular basis for your representation space, to realize this simulation. So so let me just give an overview. And I'm going to say, so This transformation semigroup is a finitely generated semigroup. In fact, it's finite, as we just said. But also we have these generators. So this paper refers to a very general theory of decompositions of semigroups called Krohn-Rhodes theory. So first of all, the realization of this as extensions of simpler groups. Or simple groups. Well, sorry. Simple group means something very specific. So simpler semigroups. I'll be informal here. And these simpler groups have been classified into various types. And then action, this transformation semigroup on this residual space for the transformer. So this is always this embedding space that you kind of always map back to for each layer of your transformer. So remember each layer, you know, somehow this is the space that has the embedding of all of your tokens and positions and everything, all the information you need. And then you have these alternating attention blocks and MLP blocks. And you always map back into this space. So this transformation semigroup is acting on this space. And then be understood in terms of a way of putting together these extensions in a structure that is called a cascade product. Is some sort of implementation of these extensions. So this is all very informal. I haven't understood it all yet myself, but I think this is the basic idea of the structure. Essentially, what they're able to do is represent these. So there's some kind of finite list of types of these simpler semigroups, and they give a construction of how to implement each one of those using a transformer. And then there's a way of putting everything together using this cascade product. So that's at least the basic structure of what's going on. Okay, so let me so let me just remind you of some basic things in group theory, just as a first pass. Understanding why you might believe that there'd be some kind of decomposition of this type. So actually my understanding of this is that things are simpler when your transformation semigroup is actually a group. Simpler in the sense that, that you have access to some more established theory. But in particular, proposed T of A is what's called a solvable group. Solvable group. So let me just recall. G is a group. So not only do you have this binary operation, but you have inverses. So in particular, the functions in your transformation semigroup are all permutations. And then a subgroup of G is said to be normal if you can treat its left cosets are the same as its right cosets. So remember that this means that that you can treat its left coset, say, as a group itself. So its quotient set, i.e. its set of cosets has the structure itself of a group. And remember the point is that normal subgroups are kernels of homomorphisms. Or kernels of homomorphisms are normal subgroups. So and G is said to be simple if G is not the trivial group. And there do not exist non-trivial normal subgroups. I.e. the only normal subgroups are itself and the trivial subgroup. So then, the ascending sequence of normal subgroups of a group is called a normal tower. And there's a theorem of the sort of first theorems we learned in graduate algebra, Jordan-Holder theorem, which essentially says that that if you have a finite normal tower that terminates in the identity such that each of the quotients are simple, then that tower is essentially unique. So let me write it down. Write down actual statement. So we're sure that these are proper reasons. The complete normal tower. So it's such that these successive quotients are all simple. Then any other tower with the same property. Then, first of all, R is equal to S. And two, there exists some permutation of the indices. Such that the corresponding groups are isomorphic. Quotient groups are isomorphic. So this is saying, the way that it is typically described is it's some kind of, it's something like a prime factorization. It's like some analog of a prime factorization. If you have the property that you have this finite tower. So groups that have this property are called solvable. They have these finite normal towers. These quotients are simple. Okay, so this is why you should believe that this is why one should believe that there are sort of natural decompositions of groups in terms of structures like this. So in the semi-group case, I think things do get a bit more complicated. But anyway, this is sort of what I'll say about that for now. Okay. So see, what do I want to say? I feel like I don't have anything like kind of complete, anything more that's kind of complete to say. But maybe what I will describe is this cascade product. And then next time I'll try to give details at least about some of the sort of simple pieces that they're actually that I can easily describe that are implementable by like transformer layers. But I think that somehow the main point is that these kinds of decompositions lend themselves naturally to being implemented by cascade products. So I'll try to put things together next time, but I definitely haven't put them together yet. So let me tell you what a cascade product is. So you have two automata, A1. And I guess the important thing here is that A2 has a different state space, but its space of elementary transitions actually includes the previous state space. And the Cascade product is an automaton whose state space is the product of these two state spaces. I mean, it's almost just like moving things around, but here we are. Where the transition map is somehow the only thing that it could be. Where it takes in pairs of states. So this is a state for the Cascade product. And delta one. It's delta one. Q1. Needs to have a sigma in there. Confused. Okay, what does it need to be? Somehow needs to be something. Oh, right, okay. Sigma.
Sigma is the state, or sorry,
Yeah.
the sigma.
Right. Sigma. Hold on a second. I think I just need to be more careful here.
Would it be delta 2 of delta 1 of Q1 comma sigma?
Right?
Okay,
Say it
so
again.
delta 2 needs to take in a Q1 cross sigma and then a sigma, right?
Delta 2 takes in a state, yeah. Delta 2 needs to take in Q2 and a Q1 and sigma. And it will spit out something in Q2. So that should be what the second component is. So
Mhm.
yeah, so I mean, delta is a map from Q1 plus Q2 to cross sigma to Q1 cross Q2.
Mhm.
Okay, so it's going to take in a pair and a pair of states and a elementary transition. And this is definitely what the second component needs to be. That's somehow the only thing that possibly could be.
And then I think the first component is just gonna be maybe, would it just be delta one of Q1 comma?
Delta,
Sigma?
yeah, sigma, yes, exactly.
Okay.
It's not the only thing it can be. Let me move everything over. One sigma delta 2 of Q2 sigma.
Yeah, that makes sense. Unless, do you want to write it as Q1, delta 2 of Q1 comma Q2 comma sigma? Because doesn't it input space Q1 and then Q2? Just change the order. I'm not sure it matters.
No, it definitely matters. So confused. Okay, so delta 1. Yeah, what's in the first? The output here should be something in Q1,
Mm-hmm.
and the output here should be something in Q2. And the inputs to delta 2 are something like this. And the inputs to delta 1, something like this.
Oh, yeah, I'm sorry. I was reading the wrong thing. You're right. Mhm.
Okay. Okay. Anyway, so now you can iterate this. You can iterate this construction. Let me keep this up so we can refer to it. And here's the definition of a cascade product semi-automaton. Iterated. Now, if you essentially do this. So you make the second state space the product of your first state space. And so, somehow you always have some standard transformation space. And then you have this list of state spaces. At level I, let your transition space be the product of your previous state spaces with this standard transition space. And you, again, make somehow there's only one thing you can write down as this transition map with respect to everything else that came before. And then the cascade product semi-automaton will be the semi-automaton whose whose state space is the product of these state spaces, and whose transition space is sigma, and where the transition map is somehow the only thing that it can be. So, my understanding is that they have simple implementations for each of these, and then are kind of understanding the overall semi-automaton as a cascade product. And then there's some sense in which this cascade is most easily implementable, or is easily implementable using the attention layers and attention and MLP layers, and also the fact that you also have skip connections for general transformers. So this is the alphabet of. So I think somehow what they're learning is from, from a decomposition which looks something like a product, they are able to define these structures of the cascade.
Wait, so to clarify, each AI is demonstrated by a transformer, and then also the final cascade product takes the answers from those transformers.
Yeah,
puts
so
them in
somehow
another
the transformer structure seems to play nicely with this kind of cascade structure. I think largely because you have attention blocks that that you can also circumvent using skip connections. Again, I'm not quite there yet, so I may be saying things that are not quite right, but this is sort of my understanding is that you decompose your semi-automaton in such a way that it's realizable as a cascade product, and then that plays nicely somehow with the transformer structure. So the informal theorem is that if A is a semi-automaton, there exists a realization of A as a cascade product. So this is kind of a classical result of Krohn-Rhodes. And moreover, we have some control over the length of the cascade and the types of transformation semigroups we see in this product. So yeah, I think somehow I probably won't be able to understand this whole thing by next time, but I'll at least be able to understand pieces of it that I can explain. In particular, what some of the simple pieces are of the, I think I want to at least understand how the cascade is implemented. And at least some of the simple pieces that they're actually able to simulate. So it's simple like smaller automata. I mean, the picture that I have in my head of what's happening is that you decompose this transformation semigroup, in some kind of standard way. And then maybe quotients in some kind of something like a normal tower look like things that they're actually able to implement. I mean, what's sort of strange to me is that the group case is supposed to be easier, but I think that even with solvable groups, it's not like completely well, it's not completely trivial, but certainly with non-solvable groups, you get non-simple groups, which I don't know the extent to which I could imagine that we can actually implement each one of those. But anyway, we'll see what we can understand.